Okay, here we go. Part 3 of the Honors Chem Final Exam Review. What is the rate law for the following reaction if you have the following data given? So whenever we're looking at these rate laws, we're trying to figure out what is the relationship between the concentration of reactants and the rate of the reaction. So it's not necessarily the easiest thing to follow in this chart because there are 3 different reactants. So you have to look at in which cases were certain reactions held constant and the other ones changed. So in the first and second experiments or trials, B was held the same, and in the fourth one, B was held the same. And in 2 of those, the rate changed, right? So 1 is different from 2 and 4, which means that the rate is not just dependent on B. Doesn't mean it's not dependent on B, but it's not just dependent on B because in all 3 of those, B was held the same and the rate changed. In trials 1 and 3, A was held the same. And in 1 and 3, you have different rates of reaction. So it's not just dependent on A. And then the trick is if you look at 2 and 4, we have A and B held constant and C is changed, but the rate doesn't change. So that means that the rate of the reaction is independent of the concentration of reactant C, which means that the exponent in the equation is going to be 0 for the reactant C. So that eliminates a couple of choices. Right? It's not going to be any of these that do not have a 0. So then the other 2 choices are the same. So now we need to figure out what is the relationship between the concentrations of A and B, and then there's going to be a rate constant that factors into this. And so what we get is that in both of these choices, A is to the power of 1, so it's a first order reaction with regard to A. But B has a bigger effect on the rate of reaction. If you look at, for example, experiments 1 and 3, A is held constant. We already know that C is not a factor in the rate of reaction. The rate of reaction in 1 and 3 is a little less than 4 times as big, but the rate of reaction, the concentration of B is not 4 times as big, so it's not a direct relationship. So we need to figure out what is the relationship between A, B, and this constant. So if you plug in the numbers that we've got, right, we know that it is the rate. Let's just take the first experiment, just because it should be the same either way. So 2.32 times 10 to the negative third equals the concentration of A times the concentration of B cubed times a constant. So if we do 0.4 times 1.2 to the third times x for the rate, then we solve, right? We have 2.32 times 10 to the third divided by 0.4 times 1.2 cubed. What we end up with is 3.35 and change. It rounds to 3.36 times 10 to the negative third. So that would be how you would solve a question like that. Okay, how can you increase the rate of reaction? Well, adding a catalyst will always increase the rate of reaction. Increasing the temperature will generally increase the rate of most reactions. And increasing the concentration will also usually increase the rate of reaction. So the correct answer here is that these are all ways in which you can increase the rate of reaction. Right, another reaction rate law question. So you're given the data here, even harder to follow because it's not in tabular form, but if you're looking at the changes in concentration, right, you see that when the two rates are different, it's the same as when the two rates are the same in the first experiment. So when A and B are the same at 1 molar, the rate is 2. When A is 1 and B is 2, the rate is also 2. So it's not affected by B. But it is affected by A. In fact, when you double A, the rate quadruples. Right? So that means A is not simply a first order reaction, which means the only one that would be correct because B, right, B isn't a factor, right, so it's going to be to the 0th power, which means times 1, which looks like you might want to say that one, but it's not a first order reaction with respect to A. It's more than a first order reaction. So the only other one that fits is answer choice 3 because it's greater than a 1 order ratio. In fact, it's when you double the concentration of A, you quadruple the rate of the reaction. All right, yet another rate law question. And when you look at the rates and concentrations here, in the first two trials, the hydrogen concentration is increased and the rate of reaction also increases. So it's not 0 order with respect to hydrogen. When you look at trial 1 compared to trial 4, the rate increases even though the hydrogen is kept the same. So it's not 0 order with respect to the nitrogen monoxide either. The fact that the rate increases by more than a 1-to-1 ratio with the nitrogen monoxide compared to the hydrogen, because when the hydrogen is doubled between the first and second trials, the rate doubles. So that's called a first order reaction. It's a direct proportion. But the nitrogen monoxide, when it's doubled, the rate is quadrupled. Okay, so we have a greater effect of the nitrogen. So we're looking for the one that has hydrogen as a first order with a 1 exponent or no exponent, and nitrogen with a second power to the power of 2 for a second order reaction. Okay, what is the correct rate law for this reaction? Again, this is the type of thing you're going to have to be able to figure out. Look at the effect of the different changes on the rate and figure out what it is. So if you look at experiment 1 compared to experiment 3, you see that we double the methane, keep the oxygen the same, the rate doubles. So that's a first order reaction with respect to methane. When we double the oxygen between experiments 1 and 2, the rate actually goes up by a factor of 4. So that's a second order reaction. Right? It doesn't look like it, but it goes from 2.5 times 10 to the negative third to 1 times 10 to the negative second. So that's actually a bigger number because it's a negative exponent, so it looks backwards, but there it is. So first order with respect to methane, second order with respect to oxygen. That would be answer choice 5 here. How does a catalyst work? Okay, a catalyst helps a reaction along by lowering the activation energy of the reaction. The activation energy, again, is you start out with the reactants. In order for the reaction to proceed, the reactants have to collide with enough energy to get over this hump, this hill, and that is called the activation energy. How much energy does it take to get over that hill? Well, what a catalyst does is a catalyst comes along and makes the activation energy lower, which means more molecules or atoms can get over that activation energy, and therefore the reaction can proceed more quickly. All right, how do we sort of recognize a catalyst when we're looking at an equation? Well, what you have to remember is that a catalyst helps, so two things about catalysts. They lower the activation energy, which makes the reaction go more quickly. The other key thing is that a catalyst does not participate in the reaction. So the catalyst is something that has to be the same on both sides while the other things are changing. And the only choice in which the the catalyst, is not changed from left to right, right? This one has no A on the right. This one has 2 on the left and 1 on the right. This one has 1 on the right and 2 on the left. So the only reaction or equation in which A is unchanged is the first one there. What is not true about equilibrium? The equilibrium constant is independent of temperature. System moves spontaneously toward equilibrium. Equilibrium is dynamic with opposing processes, and the value of the equilibrium constant is the same regardless of the direction from which the equilibrium was attained. So the one that's not true, okay, the equilibrium constant is dependent on pressure, usually. So you always have to specify what temperature you're doing a reaction because the constant is different based on temperature. Right, these other three things are true, so they are not the right answer for this question, which is not true. Which of the following is true? Okay, the one of these that is true, okay, is that when you have K, the equilibrium constant, that's large, okay, usually meaning greater than 1, then the products are favored at equilibrium. Okay, and what that means is if you think about the constant expression, you have to remember that the products are on the top or in the numerator of a ratio in which the reactants are on the bottom. So in order for this K value to be greater than 1, that means the stuff on the top has to be bigger than the stuff on the bottom, which means the concentrations are bigger, which means you've got more product than reactant at equilibrium. That's what it comes down to. Adding a catalyst to reaction does which of the following? Does it cause the amount of heat absorbed or released to change the concentrations at equilibrium, change the value of the equilibrium constant itself, or change the value of delta G or Gibbs free energy in the reaction, or does it do none of these things? Well, it actually does none of this. The only thing that the catalyst does is it allows the reaction to proceed more quickly. Okay, the amount of heat is sort of a fixed point, right? Because in order to have the reaction proceed, you've got to break some bonds, you've got to make some bonds. That doesn't change with the catalyst. The catalyst just allows it to happen a little bit more easily. The concentrations are not changed at equilibrium, they just get there faster. And the value doesn't change, and the Gibbs free energy, that's something else that we haven't even talked about. But the point is, none of those things are affected by a catalyst. A catalyst just lets the reaction go more quickly. What is the equilibrium expression for this set of reactions if we consider it as one reaction in 2 steps? Well, if we add the 2 reactions together, and we eliminate the things that appear on either side, we can eliminate the 2 ADP because that's on the product of one and the reactant of the other. We eliminate one of the ATPs on the left and one of the ATPs on the right, which means the overall reaction is ATP produces AMP plus 2PI, which means that when we remember that the products go on the top and the reactants on the bottom, the reactant here is ATP, so that's on the bottom. On the top, you've got AMP, and you've got PI, and the PI has a coefficient of 2, which gets put in as an exponent, so that is squared. So the correct answer here is this one, AMP times P squared over ATP. What would be the effect of raising the piston in this equation, which means we're increasing the volume, which would also be the same effect as decreasing the pressure? Well, do we favor the left-hand side or the right-hand side? When you're looking at an equation like this, which has gases on either side, this is Le Chatelier's principle. Okay, the stress that we're applying to the system is that we are lowering the pressure by increasing the volume, or increasing the volume and thereby lowering the pressure. That is going to favor the side of the reaction with the higher number of moles of gas. In this case, that's going to be the right-hand side. It's going to favor the NO2, since these are both gases. Lowering the pressure, increasing the volume, favors this side with more moles of gas. Is the CH3NH2 a Bronsted-Lowry acid, base, reducing, oxidizing, electrolyte, Arrhenius, or Lewis acid? Well, what happens to the CH3NH2? Well, if you look at it, on this side it's got 2 hydrogens here. This side it's got 3 hydrogens, and it's got this handy-dandy plus charge, which means it has gained a proton. It has accepted a proton, and when any substance accepts a proton in a reaction, we call it a Bronsted-Lowry base. What would be one of the products of this reaction if we assume that H2PO4 minus is a Bronsted-Lowry base? Bronsted-Lowry base, again, means it's going to accept a proton, and in order for it to accept a proton, it's going to end up looking something like this, H3PO4, which means in order for that to have gained a proton to look like H3PO4 or phosphoric acid, well then that water has to have given up one of its hydrogens to become hydroxide. And that means the correct choice here is that one, because it's either H3PO4 or OH minus hydroxide, and that's the only one that's a choice, is the hydroxide. Which of the following statements about a base is not true in the Bronsted-Lowry model? Well, the one that's not true here is that a base must be something that contains a hydroxide group. That's the Arrhenius model. The Bronsted-Lowry model is broader and includes some other things, but most of the time the OH group is a good indicator that you've got a base, but it's not always the case. The Bronsted-Lowry model does not require a base to have a hydroxide group. Okay, so this one is asking you to look at the reaction from both sides. We've talked about bases and conjugate acids, acids and conjugate bases. So essentially what we're talking about is what is the acid in the forward reaction from left to right, and then what is the conjugate acid on the right-hand side, which would be the acid going from right to left. So going from left to right, which of the species is donating a proton? Well, the one that donates a proton in this case is the cyanide, hydrogen cyanide, because it ends up as just the cyanide ion. So the hydrogen cyanide is the base, or sorry, the acid in the forward reaction. Going the reverse, if we flip this around and look at it going in this direction, the thing that's going to lose the proton, lose the hydrogen, is the hydronium. H3O becomes H2O, so that means that the reverse acid, or the conjugate acid to the base of water, is the H3O plus, or hydronium. So we've got hydrogen cyanide and hydronium as the Bronsted-Lowry acids on either side of the equation. What would be the hydrogen ion concentration for an aqueous solution with a pH of 3.45? So what we're going to do here, since the pH is the negative of the log of the hydrogen ion concentration, then to find the hydrogen ion concentration, we need to take the 10x, or the anti-log, on your calculator. So you would type in 10, hit the 10x key, and then type in negative 3.45, because you got to remember we've taken, the pH is the negative of the log. So that means when we put the anti-log in, we've got to make it a negative again. So if you take the negative of the 3.45 anti-log, then the answer you're going to get is 3.5 times 10 to the negative fourth. What is the pH of a 1.35 times 10 to the negative eighth molar nitric acid solution? Now, so this time we are just going to take the negative log of 1.35 times 10 to the negative eighth. And when we do that, we end up with a pH of 6.95. So what is the hydroxide concentration of a substance with a pH of 10.4? Okay, so the first thing we need to know or remember is that the pH and the OH are related, but you can't just take a number like the log or anti-log of the pH to get the hydroxide concentration. So the easiest way to do this, or the simplest way to do this, is to remember that the pH plus the pOH equals 14, which means that the pOH of this compound, since the pH is 10.4, then the pOH is 3.6. Those would add up to 14. Now I can take the antilog, that 10x, of negative 3.6 to get the hydroxide concentration. And that would give me a value of 2.5 times 10 to the negative fourth. Okay, last one. If we have a dissociation constant of 7.2 times 10 to the negative fourth, what is the pOH of a 0.5 molar solution of hydrofluoric acid? All right, so what you have to remember here, a couple things. We've got an acid, and we're trying to find the pOH, so we're going to need an extra step at the end where we're going to subtract the pH from 14. How do we find the pH of a weak acid? Because the fact that it's a weak acid means it doesn't dissociate completely, so we can't just take the negative log of 0.5, unfortunately. However, the actual way to do this is not the hardest thing in the world to do. But what we're going to do is we're going to go back to the equilibrium constant, and we're going to say that we've got HF, and then we're going to end up with H plus F minus. All right, so the constant expression for this would be the concentration of hydrogen times the concentration of fluoride over the concentration of hydrogen fluoride. Right? That'd be the constant. And we know the constant in this case is 7.2 times 10 to the negative fourth. So, how do we get from here to there, to pH to pOH? All right, well, what we need for the pH is the hydrogen concentration. Okay, so that's one of the things in this equation, and using what we know about weak acids and what we know about the concentration, we can get there. So, we plug in what we know. We plug in that the constant is 7.2 times 10 to the negative fourth. We don't know the hydrogen concentration, but we know that the hydrogen concentration, so that's X. We're going to call that X. We know that since the fluoride and the hydrogen both come from the hydrofluoric acid, they're a 1-to-1 ratio, which means that's also going to be a concentration of X. And then the concentration of the hydrofluoric acid is the 0.5 molar that we started with minus however many hydrogens and fluorines were broken apart. Right? So if we started with hydrofluoric acid of 0.5 molar, the concentration of the hydrofluoric acid at equilibrium is however many of those hydrofluoric acids broke apart. So 0.5 minus the X, which is the concentration of the hydrogen, also the concentration of the fluoride. So here's where it gets a little bit funky, and you just kind of have to go with it. Since it is a weak acid, very few of these hydrogen fluorides are going to break apart, or they're going to break apart and get back together very quickly. So for all practical purposes, the difference between the initial concentration of hydrofluoric acid and the final concentration of hydrofluoric acid is pretty much the same. So we're going to say that 7.2 times 10 to the negative fourth equals x squared, right, because we had x times x over here, over 0.5, because the x that we're taking away from the 0.5 is really small. So we're going to say close enough that it's going to be, 0.499999 something. Close enough to 5 that we're going to leave it as 5. So now, to solve for x squared, we're going to multiply the 7.2 times 10 to the negative fourth times 0.5. We're going to take the square root. When we multiply times 0.5, we get 0.00036, or 3.6 times 10 to the negative fourth, equals x squared. So then we take the square root of that, and we get, move this up here, we get 0.019. That's the hydrogen concentration, 0.019. So 0.019, in order to find the pH, we take the log, or the negative of the log of 0.019, and we find that it is 1.7, which means that if that's the pH, then the pOH, right, pH plus pOH equals 14. So the pH 14 minus the pH of 1.7 is close to 12. It's actually 12.3, so it's the closest to the answer 12. That is the final question on the review for the final exam, part 3, and for all of the parts for that matter. So that is it. Those are the questions you should be familiar with in order to answer the questions that are going to be in the final. And you'll get the reference sheet from the MCAS that I showed you the other day. And good luck.